Hello, students. Let's create lists of bit strings. What do I mean by that? Okay. For example, but for a bit string, I just mean a list of zeros and ones, something like that. Okay. What would the bit strings of length 1 be? Well, if I wanted the list of all bit strings, let's write down what I want to find. Bit strings of length n. So that's what I want to find. Now for length 1, what would I get? I would get 0, the bit string containing 0, and the bit string containing 1. And if I wanted the bit strings of length 2, I would get, well, I have 0, 0, 1, 0, 0, 1, and 1, 1. So those would be my bit strings there. Let's try doing this with recursion. Is there a way we could get the bit strings of length 3 from the bit strings of length 2? Well, let's think about it. What if I took these and I added a 0 to the end? For example, I could say I for I in this set. Well, that would just spit out the same thing I had before. But if I did this, I plus 0, now I've transformed these bit strings of length 2 into bit strings of length 3. But alas, these only have 0 at the end. Suppose I wanted the ones that had 1 at the end, because I want to get all bit strings of length 3. Well, I could do that, and now I've gotten the bit strings with 1 at the end. Okay, well, I can get the bit strings with 0 on the end. I could get the bit strings with 1 on the end. What could I do? Well, I could take these and add them together. And now I have just created the bit strings of length 3 from the bit strings of length 2. So that means this is a good candidate for recursion, because I can get the bit strings of length n from the bit strings of length n minus 1. So let's try to start. I think we're ready to start writing this. Bit strings n. Okay. So first I need some sort of a base case so I don't run forever and not give us any output. So we already know what the bit strings are of length 1. Let us start with this, if n is equal to 1. Okay, so if I ask for the bit strings of length 1, that's what I'm going to get. We're using the ternary operator here. So if that doesn't happen, now what do we want to do? Well, let's take the bit strings of length n minus 1 and add 0 to the end, and take the bit strings of length n minus 1 and add 1 to the end, and put that all together. So what this should do, if I say I want the bit strings of length 2, well, what it's going to do is it's going to take the bit strings of length 1 with a 0, the bit strings of length 1 with a 1, and put them together. Let's hope that that works. Hey, looking good. Very nice. Let's say, though, I want, well, let's go to 1, and let's go to 0. Well, you might know what's going to happen, because we're not going to hit this base case, because n is not 1. So it's going to try to go find bit strings minus 1, bit strings minus 2, and so on. That's not good. So what could I do? Well, let's try to rewrite this before I call that. If n equals 0, what would be a good base case? And you might think that is a good base case. It seems reasonable enough, right? You know, just saying, hey, there's no bit strings of length 0. Well, let's see what happens here. If I ask for the bit strings of length 1, that's strange. That's strange. So this doesn't look good. So what could I do here? Well, obviously my choice to not return any bit strings was bad. And why is that? Well, let's look at the process that we're using. What we're doing is, in order to create the bit strings of any length, we need to use the bit strings of the previous length. And if I have a list with nothing in it, then when I go to get the bit strings of length 1, I'm not going to find anything that I could attach to. And I need something to lock onto. So what could I do here? Well, let's just think about this bit strings 1 case. In order to get the bit strings 1 case, I want the answer to be the list of just, the list of 0 and the list of 1, or altogether the list of list 0, list 1. So in order to make this happen, I need something that I could put in this I that I could attach to 0 that would just give me the 0 list, the list with 0 in it. And the answer is to just do that. So now, in order to get the bit strings of length 1, it's going to take this and attach 0 to it to get the list of 0, and then it's going to take this and attach 1 to it. Like I said before, finding the correct base case is many times the trickiest part of writing any sort of recursive function. So now let's try this, and you'll see it's working now. And we have one that even works for 0. So my actual goal here in constructing the bit strings of length n was to actually ask the following question. How many bit strings of length n have the same number of zeros and ones? Okay, so once I've written my bit strings function, this is going to be a little easier for me to do, right? Because I know I can get all the bit strings. So what could I do? Well, let's make a function for this. We'll call them balanced bit strings. And before I answer the how many question, let's just actually write out what the balanced bit strings are. So these are going to be the bit strings that have the same number of zeros and ones. So what I want to return is I want to return the bit string, making sure I'm not using the exact same word as my function name. That would be bad. I don't want to write it over anything. So let's return the list of bit string in bit strings and if. Okay, so what could I do? I could say, okay, well, let's add up the elements in the list, and I want this to be equal to n divided by 2. And if the sum of n is equal to 4 bit string. There we go. And let's try this. I'm getting an error saying an int object is not iterable. Oh, because I summed n and I didn't sum the bit string. Very helpful error message. So I'm not afraid to have you guys see these errors. It doesn't matter if you make them, because Python's telling me exactly what I'm doing wrong, right? I'm trying to sum over an integer. That's not good. I want to sum over the bit string. So now let's try this again. And as you see, this works out nicely. Those are balanced. They have the same number of zeros and ones. Let's try this for 4. Let's try this for 6. But what if it's odd? You see, the problem here is if it's odd, it's going to round down, and it's going to give me things that don't have the same number of zeros and ones. Let's say I absolutely can't have that. Now you could say, I could just trust that my user is going to plug in an even, or maybe I'm using this for personal use, and I know that I'm only going to plug in evens. Well, in that case, this is okay to leave it as is. But if I didn't want to take that risk, I would do that. Or even just this, because I know that 1 will return true. So now, if I do that, it's telling me I have no balanced bit strings of length 3, but I do have balanced bit strings of length 4. I have no balanced bit strings of length 5, but I do have balanced bit strings of length 6. So how many balanced bit strings do I have of length 6? Well, we could run len, and we can use this to count bit strings. So I have 20 balanced bit strings of length 6. Suppose I wanted to create a function that gave me the number of balanced bit strings. Maybe not the best. Why don't we go all out with a crazy long title? Okay. And I could just return the length of what we've done before. So now I'm going to run number of balanced bit strings 4, and I get 6. Number of balanced bit strings 6, and I get 20. Now some of you might know another way of counting this. You see, I have 6 different spots, and I know 3 of them have to be 1s. So what I need to do is I need to choose 3 of the 6 spots to be 1s. And if you've had any exposure to either combinatorics, discrete mathematics, probability, and statistics, you might know that there's something called 6 choose 3, a binomial coefficient that we could use. And if we take 6 choose 3, we would get 20. And if we took 4 choose 2, we would get 6. We could actually use this to find binomial coefficients. This is not the most efficient way that we could do this, but we could use this to find binomial coefficients. So if I wanted to know 8 choose 4, I could actually just do this. And I could modify this in order to find any binomial coefficient. How could I do that? Well, what I could do is I could say, okay, let's instead of saying balanced bit strings, I want the bit strings with k sum. Okay, so now I just changed that to k. So one more time, if I want the bit strings of 4, those are the bit strings of 4. But now I can do the bit strings with k sum. Now I also need to enter k, otherwise I'm going to have an error there because I don't have a k in my argument list for the function. So now let's run that. We'll run that again for no reason. And let's do the bit strings of length 4 with sum 2, the bit strings of length 4 with sum 1, the bit strings of length 4 with sum 3, and just to not keep writing over that, the bit strings of length 4 with sum 4. So the length of this is actually what we would call in mathematics n choose k. It's the number of ways that we could pick k spots in order to place our 1s. So binomial n k. We call this a binomial coefficient. And what we want to do is we want to return the length of this function with an n and a k. So now we can find our binomial coefficient. For instance, let's say we wanted to find 5 choose 2. That should not be 0. So what is going on here? Oh, did I leave this in? Yeah, I accidentally left this in. So I said we're not allowed to use it on odds. Okay, well, no reason to do that because I want this to work for odds. We intentionally made it not work for odds. Now we're allowing it to work for odds. So now we get binomial of 5 choose 2, which is 10. 5 choose 3 is also 10. 5 choose 4 is 5. And we can confirm this. We can actually list the bit strings. Well, let's do this. 5, 4. And we can see what these are because, hey, there's only 5 ways that I can have a bit string that has 4 1s because I have to choose one spot to place the 0, and there's 5 different spots. So you can see that this is working nicely. Like I said before, this is not going to be the most efficient way for us to compute the binomial coefficient. There are more efficient, recursive ways even, to compute this. But it is one way. And hopefully you've seen some nice recursive examples involving bit strings.